Okay, so questions 11 and 12 are about the FCC structure, so let's solve both of them here. Derive the linear density expression for FCC along 111 and 110 directions. So let us draw the FCC first. Okay, this is Z, this is X, this is Y. These are the atoms sitting inside here. The corner atoms, and then we have the top face, left, right, rear, front, and bottom. 6 face atoms, 8 corner atoms. Now, first we will draw the 111 direction, which lies on the body diagonal. So 1, 1, Z, 1 is this point. If you draw it, this is the body diagonal. So there's supposed to be a corner atom here and corner atom here. So along the body diagonal, we have only 2 atoms, the corner atom at the origin and corner atom here, and nothing else, since there's no body atom in FCC. And remember that the direction itself must pass through the centers of the atom. So this is the body diagonal, a square root 3. So linear density for 111 is going to be 2r divided by, for FCC, a square root 2 is 4r, then a is going to be 2 square root 2 r. 2 square root 2 times r times square root 3. 2's cancel out, r's cancel out. This is going to be 1 divided by square root 6. And the numerical expression for that is going to be well, you can calculate it yourself. I don't have a calculator here right now. So it's 1 over square root 6. But in the answers, I think I provide that value to you. Yeah, it's 0.4082. Okay. Let's calculate the second linear density, which was 110 direction. So 1, 1, Z is going to be 0. It's going to be this at the bottom plane. So it's cutting through the corner atom at the origin, the bottom atom, and finally this atom right here, this corner atom. So this is R to R, R, and the linear density expression for this direction is going to be 4r divided by, since this is the face diagonal here, it's going to be a square root 2, this length. However, we know that for FCC the atoms touch on the face diagonal, as it is obvious from here. So a square root 2 is 4r, 4r over 4r, this is going to be 1. This is the most densely packed direction. It's made of, the whole direction is filled with atoms, 100%, and 110 for FCC is going to be the slip direction. Then we move on with the next question. Compare planar densities for 1, 0, 0, minus 1, 1, 0, minus 1, minus 1, 1 planes for FCC. So first you should be able to draw these planes. Let's start 1, 0, 0, the simplest one. Always draw your cube and coordinate axes first. This is y, this is x. 1, 2, 3, 4, 5. 8 corner atoms. Then the face atoms. Front, top, right, left, rear, bottom. 6 face atoms. Okay, the 1, 0, 0 plane is going to be parallel to y if you take the reciprocals, infinity, infinity. So it's going to cut x at the edge along the vertex, and it's going to be parallel to y and z plane. So it's this front plane right here. That's 1, 0, 0 plane. Next, what do we have? Minus 1, 1, 0. So minus 1 is 1 edge length behind here. So if this is 1, sorry, for x direction. So if this is 1, then it's behind the cube, minus 1. It's also going to cut y at 1, and it's going to be parallel to the z-axis. So if you draw that plane inside the cube, it's going to look something like this. So normally the minus sign forces you to draw it outside the cube, but you can bring it inside, and it's going to be something like this. So let me draw with a different color. This plane right here. This is going to be minus 1, 1, 0. And finally we have minus 1, minus 1, 1. So it's going to cut x and y at minus 1, sorry, let me draw this once more. Z, X, Y. Okay, minus 1, minus 1, 1. So go 1 unit X to the back, 1 unit Y to the back, and 1 unit Z upwards. So minus 1, minus 1, 1. If you draw it inside the cube, it's going to look something like this. So one thing to notice, this looks a lot like the 1, 1, 1 plane, which we drawn before. So if you draw both 1, 1, 1 and 1, minus 1, minus 1, 1 as a 2D projection, it's going to give you the same picture, okay? This. Similarly, for this minus 1, 1, 0, it's going to give you the same picture as 1, 1, 0. That's why these planes are called family of planes. So the density of 1, minus 1, 1, 0, this plane, is going to be exactly equal to 1, 1, 0. Similarly, minus 1, minus 1, 1, that's going to be exactly the same as 1, 1, 1 plane. So the calculations that we did for 1, 1, 1 plane for FCC, 1, 1, 0 plane for FCC, which was in a previous question. So let me find that. So this, okay, this is going to be exactly the same calculation here. Same for this 0, 1, 1 is going to be same as 1, 1, 0, and that's going to be same as minus 1, 1, 0. So I'm not going to repeat those here again. This turned out to be 0.9069. This turned out to be 0.554. We know these. Then all we need to do now is calculate the density of 100 plane. If you draw the 100 plane, it's going to be composed of these atoms. Okay, these are filled. So the plane has the edge length A, it's a square, the front square, as in here. Okay, so the area occupied by the atoms, pi r squared times, we have one atom fully inside the square there, plus 4 corners, 90 divided by 360, that's going to be 1 over 4, divided by a squared, that's going to be pi r squared times 2, divided by a is 2 square root 2r. If you square this, you will get 8r squared. Okay, simplify this to get pi over 4. Then rho 100 is going to be pi over 4, and that turns out to be 0.7854. So this plane is the least densely packed. Then it's going to be this plane. Then it's going to be this plane. This is the most densely packed plane.